I titled my lecture Architecture Unplugged, and it's a couple reasons why I did that. It is borrowed directly from the rock and roll scene, right? Now it's a pretty common thing to think of unplugged, but in the 80s it was a very new idea that MTV started. They started this series called Unplugged, where the bands or the singers would actually move back to the acoustical guitar and unplug their instruments and really try to get back to the origins of their music. And in some ways, that's what I also propose as an idea for architecture too, is that we have to start to look back at our origins of architecture, one, and then two, which you'll see later very obviously, look at more literal rendition of Unplugged, of literally trying to move away from energy sources and using energy in our work. So as we look back to architecture, and this is obviously the common image that we use, but less philosophically, more tectonically, we start to think, okay, in the past, things have worked very well. They've actually been quite smart. They've had different materials. We look at things like the igloo, right? The igloo is a very simple, very smart structure. It's a dome, so structurally it's very strong. It's a shape that the wind can move over very easily. It's a local indigenous material. There's a lot of air bubbles in it so that it can perform very high, at a high level, as an insulator. And then even on the inside, when you use the fire and heat the inside, the inner surface actually melts, and then the water, as it refreezes, closes up all the cracks to reduce the amount of water entering. There's also other things like the yurts, right? We have the goat skins, the animal felts, the layering of it, the portability of it, the breathability of it, the waterproofing, all these different things work very well and don't require a huge amount of technology to do it. There's a very low-tech attitude to it, and for many, many years work. But the problem is, we can't really build our houses like this, right? Depending on where you live, there's no ice sitting out in the yard here, or some pelts hanging around. So, because of our industry too, we're dependent on labor and man-made materials. But in a way, we want to try to look back at these very simple ways of building, producing these materials, and manufacturing them. Our dilemma, too, as you all know, is very simple. There's a lot of energy use going on. Over 40%, it's actually, this is a conservative number, of all energy is used for buildings. And in those buildings, you can see it's broken down into three basic categories: HVAC, lighting, and equipment. HVAC being 45%. Out of this percentage, you would think that if we can try, as a research level, to invest more and more money and time and effort into reducing even 1% of any of these things, it would make a huge change in our energy usage overall. In addition, we have problems like the heat island effect. You all are probably familiar with that too, with the cities, maybe not here as much as where I'm from in LA or New York, and especially places like Tokyo, where around the city there's almost a bubble of hot air that gets hotter and hotter every year. And because of all the hard surfaces, what happens is in the evenings, it can't cool down. So the normal cycle is at nighttime, it cools down, the daytime it heats up, and you keep recycling it in that way. But the cities now can't do that. So we have these hotter and hotter areas, and that situation is exacerbated by the use of air conditioning units. So as you know, with air conditioning units, in order to cool the interior, it has to spit out hot air to the exterior. And so as this is multiplying the problem of these cities heating up. So I started to look at smart materials. It was probably about 7 years ago, and I thought, well, why don't we start looking at smart materials? The materials that virtually need no energy, no controls. That's one of the biggest criteria, but they respond to some change. They can respond to temperature change, humidity, other variables, but they need no controls to do it. And so I went on a search to look at different materials, and I'm going to show you a lot of the projects that I do. So this lecture, the second half, will go into several projects using that material. But what I want to talk about briefly is this idea of smart. Not only is the material smart, but there has to be some intelligence in the use of that material. So, for example, the geometry that is cut, the method of cutting it, the way that it's applied, the way that it's aggregated, and also the way that it's actually used. Makes a very big deal. So smart use, smart design of a smart material is a really important correlation to have to make. what I want to talk about too, very briefly, is what's not smart, because we use the word smart a lot in a lot of products, a lot of things that are out there. Everyone likes to use that word smart everywhere we turn. So there's smart water, and as you know, I don't even want to get into what is not so smart about this, because I still can't figure out why it's called smart water. Although it does say here, see, I'm not afraid to spill. I don't know if you see that in the very small print here. Maybe that's supposed to be the smart part. Smart cars, right? Not so smart necessarily in this case. I guess it's smart just because it's small and just by size alone will save gas and space. Smartphones. Smartphones, I mean, in some ways we can say that they're smart. They're smart operating systems. They provide a lot of things for us that we can't necessarily do ourselves, whether it's from, you know what I mean, using a calculator to GPS to all these different things. And we call it smart because it can add and augment. But there's a huge requirement for energy to run these things, right? If we run out of power and stuff, then we're lost because we don't have the smartness with us that we're so reliant on. And finally, if you go on the internet and you look up the word smart house, these are the things that you will see on the internet. And the smart house is defined, unfortunately, by the fact that it has a lot of gadgets here, right, as you know, all these different kind of controls used by either remote control or by sensor systems. But the problem is, truly, this is not smart architecture, because we still have the same ceiling, the walls are no different, the floors, and the architecture around is identical. So can we truly call this a smart house or a smart home? And that's some of the questions. But the systems that are really truly smart are obviously things that are nature. And the human skin is something that can respond and do a lot of different things. It can sweat to cool. You have goosebumps to heat you up. They inflate. It is self-cleaning. It is waterproof. It can, you know, make certain kind of levels of melanin to resist sun or not. It could do so many different things, right? And do it very efficiently as the first line of defense to the human body, so that, in effect, your heart, your lungs don't have to work so hard because of the skin. So these are the systems that become very smart, and we start to look at as a man-made material or something to try to mimic. So you see here, too, in shark skin, right, the swimming shark skin thing that we're starting to mimic the actual shark skin or the way that it moves through the water, and there's some intelligence to how this is actually applied and developed. And there's other systems that we need to look at too. Like in this case, it's the social weaver bird out in the Kalahari. These nests are humongous, and you can see these holes in the bottom where the birds enter. And they're very resourceful, because you see in this case they're just trying to use these telephone poles to build on. But these holes, if you can imagine on the inside, the very center area of these very dense nests is the coolest areas that can be used. And those are used for nesting, for other purposes, whereas the outer edges are used for different social purposes. And so the layering system becomes very smart and intelligent on how it's used and applied throughout. You've probably also seen, too, termite mounds. Termite mounds, you don't think of termites as being very intelligent animals, but their system and instinct of using these things is really quite amazing, because if the mound itself gets too hot, what they do is they unplug a few holes in the top and the bottom and get natural ventilation to vent out the heat. And if it's too cold outside, what they'll do is they'll actually plug those things up again, too. So systemically, it becomes a very intelligent system. In the past, too, for architecture, right? Again, there's certain intelligence to what this was, and this is pre-air conditioning period, where the walls were very thick, the windows are very small, it's highly insulating, but somehow during the hot summers, the interior was cool. And during the cold winters, the interior was warm, and the insulation value from that, just from the thickness and the mass of the walls, were able to do that. But then technology came, you know, more man-made materials, perhaps the use of it not so smart or intelligent at the time, but amazing, is, again, plate glass, right? The plate glass, long-spanning steel, and what you get is floor-to-ceiling views out. The windows now were enormous, and the connection of man with nature, at least perceptually, was closer, even though the glass was oftentimes closed, and from there we started to invent something that would allow us to keep this even further, which is the air conditioning, HVAC type of systems. So from there too, And because we're unwilling to give up this condition of 180-degree views, the air conditioning systems got bigger and bigger. Elevators made us go taller and taller, and now we have these 50 to 100-story buildings, which is really quite amazing if you think about it, that are air conditioned, that we have floor-to-ceiling views, and we keep insisting on building these things. But I'm sure you've all been into buildings where if you're sitting on one side or you're sitting on the other side, the temperature is very difficult to get right. It's either too cold, too hot, something is quite wrong, and on top of that, you can't even open a window. So the dilemma is you have an energy problem, power outage, basically everyone has to evacuate the building. It is completely unusable. So, as I told you before, I started using a material called thermal bimetal. And thermal bimetal is a smart material. It needs no energy. Here you can see it's being heated up in a chamber. It curls automatically when heated. And what it is a lamination of two different metals together. You can see here, and as it's heated, it's a very simple process. One metal expands more than the other, and therefore the action is a curl. So I decided to try to use this, and the first project I attempted to do was a ventilating surface. And this ventilating surface, I just wanted to see if I can make a surface out of this material. I'll show you a little later. The material comes in these big coils, and the coils, although can go on and on for thousands and thousands of feet, are only 6 to 12 inches wide. So in order to use it as a material, as a surface, you have to use it as a tessellating system where you use a lot of small pieces, or somehow we're trying to also manufacture ways to make it wider. But the ventilating surface, the idea was, again, trying to get this thing to curl inside and just open the surface altogether. And when I started this project, it was about 2008. Even the manufacturers thought this was like a crazy thing. I haven't, you know what I mean? They said, this is preposterous, you're never going to make this happen. The material is normally used as a coil in a thermostat. So it's used as a very small piece in a very small condition in the interior, hidden in a box somewhere that you don't see. That's the residential type of thermostat. It's also used for automobiles, for industrial equipment, as emergency turn-off systems, switches, etc. But it's something that we've never actually used or thought of as a surface before. So combined with using different digital technologies at the time, in this case this was using CATIA. And CATIA was really useful for us because Grasshopper was not developed enough so that we could not tessellate an entire surface and actually go down to a fabrication process. So we used CATIA, which was a very, very heavy type of model to do at the time, but it worked quite well because we connected every dimension on each of these tiles to the location on the surface. I do want to point out, you can see very carefully that we had to number all the pieces. I'm sure you guys have had to try to do this before, because when you have so many pieces and each piece has a specific place, you need to know where it goes when you put it together. But I want to point that out because, again, it will show up a little later in another project. And this was that surface. So you can see the surface itself. What he tried to do here was make some of it vertical here on the side. These pieces were more horizontal on this side, and it was just, again, it was this kind of proof of concept, trying to see if we could get anything to move, to see what friction was going to provide for us as a problem, and also gravity. So the original idea was to make this all vertical here because I wanted to see if any of it could work to pull up this bottom length at all, if it could curl in sequence to try to shorten that, and we found that it couldn't. And that part wasn't as successful, but you can see here in the sequencing of the photographs as we heated the side, and these are the horizontal pieces that over time it could change quite a bit. Then after that, because of the failures, again, I'll show you some of the successful and some of the not successful parts of our work. I wanted to try to do things that were shape-changing. It's the obvious thing. A lot of people said, oh, well, there's a whole thing going to move. And I said, well, not really. But it was still, it's one of those things that in the back of your mind you keep thinking, well, maybe we can do this. And so we keep trying. And I'll show you 2 projects that we tried over. This was a project that was used for the wintertime in New Orleans. And in New Orleans, it gets pretty cold in the wintertime. And at nighttime, very, very cold. And they wanted us to use this material, and I couldn't figure out how to do it. So What we did in this case is we did have to plug it in because we had to use heaters to heat it up to make this thing move. But we used the heaters as a source of heat for people to gather around and to move around like a campfire. And the idea was to try to open up and change the shape of the surface by making these slots emit the heat. As it got hot inside, you would basically have the heat coming out. And so here you can see it during the day. Nobody actually saw it during the day, but the view that they all got was actually during the evening, is the one on the right. Here's another project. Like I said before, we keep trying to make things change. This is our idea here was to use a slinky. You can see the very colorful slinky that we had to order. It's about an 8-inch diameter, and we heated it in our testing box, our testing chamber that we made. The problem that you see here, as I told you I was going to show a few of our failures, is our slinky, which is made out of plastic, melted as we're trying to heat it. So you can see it has a sag after it was done, which was a little disappointing for us. But you can also see the thing actually shrunk and actually could change shape. So that was a successful thing. And so we then turned it upright. You can see our melted slinky here as we cooled it and it rehardened. Was changed, and we heated it from one side so that we can see if we can get this thing to twist. And the reason why we use the slinky too is because then I thought, well, we can make this any kind of length possible. We can make this like a snake and control it, moving it, as well as the idea of a spiral. In the case that this is a slinky, the slinky was identical in its coiling, but because of laser cutting and stuff, we can actually change coiling. Because of 3D printing, we could do all these different things. So this was the first step to trying to think of how to deal with that and try to make something change shape. This is another project where the shape changing is a sphere. You can see here. The pieces were open in this case, and so the sphere is very large. As they close, the sphere itself starts to shrink. You can see by the dashed line around it. And the units are here at the bottom. Are open and closed. They're also made out of the bimetal. You can see here, this is pretty close to real time. So we're heating it up. You see it closing, and then you'll see it snap back as it cools. A lot of our testing area is done in our heating chambers, sometimes with a heat gun, sometimes with a blow dryer, basically anything that we could find. Oftentimes it's done outside. Because we're in Los Angeles, like you guys here, we have a lot of sun, and we can use that as our source. So here you can see in the top the array of putting these together, and the diagram here where you can see it open and closed if we can array it even bigger. The question that we're trying to consider is what scale we operate this as. One of the things that we're thinking of is in a double facade system, is that this system could be its own kind, a different kind of shutter system. Instead of the typical blinds that you get, we can make these shutter system fairly decent size so that we can cut out a lot of sunlight as it enters the building. I also worked on this sun shading canopy called Bloom. I think it was referred to, you guys might have seen it before. This was completed about 2 years ago and was about, I think at the highest point, almost 22 feet. It was in Los Angeles, and it was designed to be a big sundial. The idea behind it is that the different surfaces would be able to shade in different ways or to ventilate out, and to make a pavilion so that we can make it very public and people can actually experience and see how this thing works. The thing that was exciting about that as a sun shading thing for us is that we can actually test it outside. So we located it at a specific location through our analysis. We connected all the models together. We worked with engineers to get the lightweight structure together, because again, to make a 22-foot tall structure, you'd be surprised how much structure you need for that and how much light would be blocked from it. So we worked with Burl Happold on a monocoque system so that we could minimize it. It was extremely lightweight. The rendition that we built probably added up to maybe a little over 500 pounds only, the entire structure. You can see here there was a whole assembly process because we wanted to make it very simple, because all we had was basically student labor and no fancy tools possible. So it was pre-making these things, numbering them again. In this case, this project had about 14,000 pieces. Over almost 10,000 of them were bimetal pieces, and about, I think about 4,000 were the structural pieces. We went through a huge number of renditions of the tiling and what kind of tiling was going to work and how we were going to attach it and how we were going to assemble it, make them work. I told you before, geometry is a huge thing that we deal with now, and I've learned this over the years, how much math I now have had to use. I know before everyone, when I worked in a conventional office, I'd have people, non-architects, say, well, don't you need to know a lot of math to do architecture? And I'm thinking, well, no, right? Because AutoCAD's going to, add all this stuff to it. I'm telling you, this is just amazing because now we're using trigonometry, we use calculus, we use, algebra, we use all these things to calculate a lot of our surfaces and tessellation. We made diagrams of the different times of day and the angles and different times of year of the sun itself and how it hits the surface. And connected them all so that we whittle it down to two pieces. The length of the, what we call the tail here, you can see, would be short in areas that the sun would never hit and very long in the sunny exposed areas. And the second part was this portion at the top that was connected and the width of that. And so that determined the ventilation in certain areas or the amount of light that came through. You can see here's some early paper models of putting it together. In some cases, we tied down all the pieces because we needed more structural capability. So when we tied it down, these panels became structural panels, and we had to determine where they were in our entire model. So with Ecotect, you can see the color zoning was connected with our grasshopper model. This is when we did flip over to grasshopper and did it almost fully grasshopper. Here's the first day. We started sorting, and this is one of my favorite parts because we were so excited to get all the pieces. We're sorting it all out. We went to lunch, came back, and everything was curled up and messed up again. And so we had to go back through and sort it, and we just, again, you don't think very smartly about how these things are going to affect the operation of it, which also, I'll just point out, when we installed the thing, even though it was in November, there were some hot days and very sunny days in LA. And so all our panels would curl up so that we would get cut sometimes because we're trying to install it and the pieces are, they didn't look as simple and flat as this. But they actually, I'll show you right now, they get curled, and so installing them became a little more difficult. So you can see even with the blow dryer, it operates fairly quickly. It'll take a few seconds, depending on the heater. So you can sort of see how it starts to change and starts to curl up. So we also came up with an innovative way to build the whole thing because we didn't have cranes, we don't have a lot of money to build this thing. What we decided to do was build it from top down. So we got some very inexpensive lifts to lift the corners of it. We built a ring and we basically started going in spirals all the way down and kept lifting it up until we let go. Oops, sorry. So you can see the day and night from the front here. You can see in some areas it's very porous where the tails are short. Here too, in the night view though, you can see it almost becomes transparent because that's the south side of the project where next to the building, the sun never actually hit the surface in that area. And different views of it. So here you can see, for example, is a structural panel where everything is tied down. And we combined a little aluminum in there too for more strength. And here you can see this is the first time that we actually saw this surface operate because we put a time-lapse camera there over the course of the day, and this is in January. You can see January 5th in Los Angeles. And it wasn't that hot, but it was quite sunny. And so when we finally put our time-lapse together, it was the first time we actually saw the operation. Because the problem is when you're standing there, the temperature's not changing. You don't see the surface changing. You're like, as long as you watch it, unless it's going to drop 10 degrees, it's going to look identical. So the idea behind this was to try to apply this to, as a brise-soleil to buildings. So in this case, it's a building in China. You can see here in the red, this part was a tower, or it's just a three-story portion that was glass. And in order to try to control the amount of air conditioning, we wanted to put the bimetal on the outside, right, and make it a brise-soleil. We connected to the program on the inside, depending on whether it was a private program or public. We used it so that they did not have to use any curtains, that they could get privacy in the evening, get control of sunlight on the back side, which is the south side. And that is, we're still waiting to go into construction with this. It's in a man-made lake up outside of Beijing. Tensegrity model. So we're trying to look at ways to combine this with structure too. The structure is the combination of like tendons, bones, muscles, and you put all these three things together, you can get the things to possibly operate and move. And so the idea behind it is to use, oh, I just missed that. But anyway, this is nitinol. It's another smart material. It's a wire that also reacts to heat. Basically, it is a nickel and titanium combination. In this case, the material shrinks when heated. And the problem with it is, unlike the bimetal, which you can see goes back and forth, you have to stretch this thing out. So you can see the hand of the person pulling it out before you put it in hot water, right, and actually shrink it and form. But the idea is to combine using this into a tensegrity model so that we have this kind of unit that we can multiply. The idea is to use what you see in the red as the bimetal so that we could turn it, rotate it towards the sun when necessary, and the system could automatically adjust itself relative to the outside heat. The bimetal in this case would be the tension to pull the nitinol back out. You can see here is a combination of that system, and although it's exactly in the same position, just going back and forth, you can see the change in movement of those lengths. So we're hoping, we're fundraising for this so that we can get funding to actually build it. Another project, I mean, we keep going through again, every time we build something, we keep having these new ideas of what we can do with bimetal. And the nice thing of what I do is we have the luxury to keep testing these things. So this idea was working with was collaborating with a friend who basically hacks 3D printing machines up at Berkeley, and he is able to make a concrete polymer. So with him, we tried to make this kind of breathing wall system. It was the idea behind making new types of cinder blocks, right? The cinder block being, again, a very basic building material, and very inexpensive. So now that we can do the 3D printing, they don't have to be identical, they don't have to be blocky, they could be something else. And so using ideas from this grasshopper and how grasshoppers breathe, what they do is they contract their diaphragm and they suck in air through these spiracles from the side, and that air moves around their body system, cooling and bringing oxygen in. And so the idea was, why can't, again, a building wall do that? If we can 3D print these blocks or cinder blocks, can't we also make air move up and down through the system? We can use things like the Venturi effect or Bernoulli's principle to get air movement, to get air to speed up or to be constricted, and use the bimetal as plugs to control, so that the bimetal itself, when they're open and hot, can allow the air to pass through. You can see here, but when it's cooler, to shut down and make more air cavities in it, so that the air cavities in itself can combine to make the insulation. So you can see here, again, trying to use all the different laser cutting, 3D printing framing, the 3D printing of the concrete to build this small proof of concept idea. And you can see the red light is an infrared light for our testing. As you see it heat up on the bottom, it moves through in a diagonal or a zigzag method of going through these cavities. It's not stacked literally on top of each other. So you see the bimetal opening and closing in this effect. Again, with computer programming here, you can see that it can go on and on forever. It's a very small segment of what the wall was that we originally conceived of. But it was actually a very interesting and is probably going to be picked up because they want to start to developing this at a much smaller scale. So what we're trying to look at, a lot of the things that we do, unlike architecture, you make a small-scaled model of something that's very, very big. In our case, what we're starting to learn is a lot of what we do is we make a lot of things big in order to think small. So some of the projects that we're working on are considering it at micro scale, possibly at nanoscale if the technology is out there. So we're starting to work with some engineers in those divisions to develop those materials. Window shading. This seems like a common idea. Like I said before, the bimetal I want to use as a brise-soleil on the outside of the building to control the heat before it enters the building, and that's probably the most efficient way to deal with it. The problem that you run into is you got to deal with like building permit office, right? And all the wind loads and testing because it's on the outside of a building. In a double facade system, I showed you before, the hexagonal system that could open and close is a little more safe because you don't have to worry about those building code things. But you have a maintenance issue. But the last way is to consider it between two planes of glass in a window system. So in a double or triple glazed system, you might have seen, again, blinds that come through in those systems, but the idea is trying to put the bimetal between it as well. And so here's a typical condition, right? You have, again, the floor to ceiling windows. You have heat gain. No matter how much you tint those windows, you still are going to stand in the sunny part and you're going to feel that heat. But the idea, like I said, is between the two planes of glass, put the bimetal, and the bimetal, when it gets hot enough in the planes of glass, will actually shut down and provide a lot of shade, and we'll do it automatically. We're working with a company in Spain right now because our problem with this is how to cool that chamber once it's hot, right? So once you heat it up, we can just hope it cools down at night, but it may not. And so, again, using the bimetal to ventilate it, it opens up, ventilates it out so that it could reset itself for the next day. But it's a different problem for geometry for us because now it's a pattern issue. Instead of making all these tiny little pieces that is going to be impossible to attach, we have to now consider using the bimetal as a flat sheet material and apply these patterns. So this is a very, very early pattern that was very promising to us because we didn't know that the bimetal would actually operate as a surface and curl in many directions. Again, the manufacturers never tested anything like this before. They couldn't even tell us what would actually happen. So we started making these very early models. You can see here, we start making more complex geometries, and the geometries that we want to do is always a balance between aesthetics and function. Because, again, you put these up on a window system, you want it to look good, you want to know the extent of what you can do aesthetically as well as performatively. And so in this case, these things are actually quite big. You saw the head of a heat gun, which is not that different than the size of a blow dryer. But these are the patterns, too, that we're trying to work on getting to a micro scale so that they'll be hardly perceptual in some cases so that you may see things more or less transparent over time, or they can be in the case that you need a lot of coverage. You can see, again, with digital tools, you can make them translate from one type to another. Again, we're working, we have so many patterns that we work on, but trying to hide the system behind it so that you don't look at it and you look at the metal thinking, oh, well, it's going to curl this way, it's going to curl that way, that you actually just see it as patterns and start to look through it. So it's a perceptual thing as well in these flat, surface-like bimetal pieces. This is an animation because, again, the idea is trying to make that surface operate so that, again, without the use of any controls or energy as the sun passes through it at certain times of day because of the geometries, and we couldn't do it in this animation, but the geometries itself could be affected so that they can operate differently throughout that day. Structural surface. This project we just got a R&D award in Architecture Magazine this summer for this project. I'll just tell you really quickly, the idea behind this is one of my employees is from New Hampshire, and he does not like it in LA because it's always hot. And he does not like that we have to do this project for heat. And he wants to do this project, which you might have heard, there's a competition up in Manitoba, Canada, which is to make these pavilions during the winter time for ice skaters to go from station to station. So he keeps every year asking me if we could do this competition. I said, well, no, it's freezing cold there, this is not going to work. And so he's been bugging me so much that I said to him, well, the only way that I would do something like that, because I don't like cold, is if I could use a blowtorch, I could get like head to toe covered with it and not, you know what I mean, expose my hands or anything and stand outside for 8 hours. And so if I could get a blowtorch and torch this thing up and the whole thing could self-assemble, then maybe I would consider it. And so that was kind of the genesis to this project. Although this is not a project for Manitoba, it was the idea of trying to make something self-assemble in some ways, or the first steps to assembling and making assembly easy. And in this case, you can see, and I'll show you photographs, it is an assembly process that you end up using gloves anyway. So the idea is not that far off. But you can see in a thicker piece of bimetal, it becomes very structural. They're actually very difficult to bend. It's not aluminum. It's a nickel-based material. So it's kind of between aluminum and steel. But when you heat it up, it bends really easily, right? You pull it out, it's all bent up. There's no way I can actually physically bend it. And so using that heat during the process, what we could do is we curl it, we put it into place, and we make a pre-tension surface out of it. And by combining it and weave it all together, it makes a very, very lightweight, very strong surface. By changing some of the curvatures, we can make it curve in one direction or another. And this was the first proposal. This was proposed to be built at MoCA in Los Angeles in 2013, a little over a year ago. The problem with MoCA is they almost went bankrupt. They almost shut down. They had really big political headaches, so we never could build it at that time. But what had happened is the Museum of Contemporary Art in Santa Barbara found out about the project and they wanted to pick it up. And so what we did is we started to go into design development for the project, realized that we had problems inverting the surface. So, sorry, you can see here this surface had a curvature going in this direction, but then reversed its curvature as it moved up here. And what we found is we could not get rid of the seam line between it. We could not make it seamless, and therefore did not want to do that. It just was not aesthetically appealing enough to us to even pursue, even if it performed well. And so what we decided to do was make it a curvature in one direction and wrap it around itself to even be stronger than what we even thought. So we were making a structural surface, and with our engineers, and this was where we did this with Arab engineering, we decided to try to push the limits of the structure. And the idea with engineering is there's two basic things in architecture. You either make a beam or you make a column, right? I mean, it's very, very simple. You make a bridge or you make a tower. And so what we decided to do, because of the venue, was to try to make the tower. And so what we did was we made the bottom tier of what was supposed to be a 5-tier tower. Again, like a lot of our projects, we have very low-tech labor, and we don't have a lot of tools. And so we made it into multiple tiers because that way we could stand on the ground again and build the whole thing, not using scaffolding, not using anything. And so each tier we could build, we could lean it, and then tilt it up again. The dimensions of it were determined by our own body, again, so that however far we can reach into it. The bottom one we can actually stand inside, and we dimensioned it to allow one person to stand inside. But the rest of them were determined by arm's length and how we put this whole thing together. Early study models tried to see if this really was going to be structure, if we could put it together, and it was surprisingly successful at that time, so we kept going. More study models. This is a small model that's about 2 feet tall, but it actually used thermal bimetal to scale, and we wanted to test the tension on the outside using just plastic to see if it was truly relying on that or not. And it very successfully held in tension. The final material we used for the outside was aluminum, and you can see in the model here in the colored, you'll see it more. All the colored pieces are all aluminum. Those represent the tension, and the bimetal is on the inside. So you can see here's what I was telling you about the gloves. With the gloves, you can get that heated or the hot piece of material. You fit it in, and you let go, and it cools, so it flattens out. Oops, sorry. Here you can see the inside as the piece is going. We just did it in rows. And the assembly process. You see, we hung all the pieces, the aluminum pieces. You can see them very, very loose. It almost was an hourglass type of surface. And as we put in the bimetal pieces, one piece at a time, it starts getting more and more taut, and you see it just tighten up as the pieces get filled in. And again, you see, the scale was designed for one person to go inside. The thing that we didn't figure out, here's part of the failure of this one, we didn't figure out how to get him out after we finished. because this piece was surprising. I mean, it's 200 pounds, which was lightweight for its size, but we had to pull him out from the top, and that was a pretty funny thing. And here you can see as he's pulling out his glory moment of actually testing the structure itself. And transporting it to Santa Barbara Museum, and here it was standing there. So on the outside it looked really quite different. You see the color aluminum, and then on the inside all the bimetal as you look down the center. This model turned out to be very useful because the clear plastic allowed you to see all the bimetal on the inside. We only built one tier because we ran out of money, basically. So we're fundraising to build the other tiers. Here you can see the height is supposed to be around 40 feet height. More recently, we're working on more assembly strategies, right? The material itself comes in these coils, and the coils I said before are 6 inches to 12 inches wide. You can get thousands and thousands of feet on a coil. The problem is, when we cut it down to all these different shapes and sizes, we get 14,000 pieces. It took us over a day to just sort all the pieces and to keep them all apart and to number them and to deal with that. And so we were building a piece for exhibit for this conference in Germany. And I thought, oh my God, we have to go there and take days to just put this together just by sorting it. So why can't we design this thing so that it's just one piece, right? Why can't we just do it so that it's like, you show one piece, you put it all together. And so what we did from our Slinky project, you remember the spiral, is we thought, well, why can't we just put it together as a spiral? Why can't we just, coil it and design it so that it is all virtually one piece and that you could, connect it all together. And so that's what we did for this one. You can see the surface is actually all coil. I mean, the whole thing is coiled all the way around, but you can't see the coils when it's done. You can sort of see the rotation of the geometry as the pieces start to rotate around the surface and the surface itself. So this piece is going to have a heating device on the inside, and it's going to operate, so the flaps are actually going to curl on the inside. On the outside, you'll be able to see through into these holes to see the heating elements themselves. And we're also doing self-assembly even more, so that in this case you use no hands, no people, no hands. The intelligence is in the cutting and the geometry of the thing itself. We're in the beginning stages of trying to make this work, but there's some success to it. So just by the cutting, you can see that we can make it fit into slots itself. We can make a chain out of these elements. You can see the point that, like right at this point, is when we heat it up, and now it's cooling, so it'll lock back into place. These are small, and they can go even smaller. This is real time. This piece is probably about 2 inches square by 4 inches. And the idea behind this is possibly making things that we can't get to as humans, whether it's in a hard to reach place, that the scale of it's either nano scale or too small to use tools, that it's in extreme conditions, whether it's out in the middle of a desert somewhere or outer space even potentially. We've been approached to consider it for even moon technology. Seems a little far off, but it has a lot of potential. Again, the scale is really quite different. We're working on a lot of different things that I can't really show you at this time. I can't show it because there's disclosure. You guys would all have to sign disclosure agreements to see it. But here again is the idea. It's also something that we can possibly use in flat systems and array it, because we can get a very high differential between the percentage coverage and the emptiness of the result. The last thing I'm going to show is this is a fun little project that we do on the side. We make these little critters in our office. So we have these races. And everyone has, and it's probably the slowest race you can think of. This is a little fast, it's about double time. And this would be the amount that this would move over the course of 2 days, right? So one day was one somersault, and the second somersault is the second day. And so we would actually put them outside, and we'd have these races who can go farther. And it's the slowest race because each one only moves a couple inches at a time. And some days when we get back, it has blown, you know, off course, or or the dogs have taken off with it. But it's really critical, I think, in some ways, because now it's also talking about using, you know, solar energy to power something, to actually make it move, to make it have a life of its own, to have a personality too. So even in our office, we actually narrate our little sequences, and we talk it through and make all kinds of sound effects. But anyway, we have a good time, and it's a lot of fun. It's great exercises. So when students come work for me, this actually is one of the first exercises they work on to really understand and learn the material. But thank you very much. That's basically it. Questions? What are the questions? Yes.
Are you accepting donations?
Yes, absolutely. We are it is funded primarily through grants and private funding.
I was going to say I have $1.
Okay. But we could pass around, you know. Any donations? Yes. Yes.
On the project that you brought forward, is there any complications transporting it outside of the sun?
No, because that material is thicker. The thicker the material, the higher temperature it operates at. So it cools between 250 to 300 degrees. So our problem with it now is we can't get it out, because in order to get it out, we have to heat the entire thing, and we can't, I don't know how to heat the whole thing quite yet. That's when the blowtorch comes back in again. Because I think if we can get it hot, it would just disassemble itself by, I mean, it would just all, you know what I mean, drop off. But that's our next step.
Is there any exploration with gases, nitrogen, hydrogen, any reaction not only towards heat but to chemical heat?
The one thing that we are working with, we're trying to make the material react to humidity. And in order to do that, we are using, I can't tell you what it is, but coatings that will react to humidity. So that what happens is, because it's lower, you feel hot in lower temperatures, so that the material will not necessarily curl at that low temperature, but in order to raise that temperature, the application would make it operate at a lower.
Okay.
Yes?
Have you gone into depth regarding the acoustic properties of this material?
No. But you know, it has, what we haven't really done quite yet is we can laminate the material to a lot of other things too. Right now, the lamination process for the two metals is actually a crushing process. So it's a molecular bond. There's no adhesive, there's no nothing. It's just crushed with big rollers. And that's why it can stay like that virtually for the lifetime of the material. In most cases, the adhesive is the thing that breaks down first. But what we can do, and we're looking at it because 3M is developing adhesive that I don't know if you've seen before. It's really very cool. They have tape that they claim can tape a facade together. And they've been using it already on taping some metal facades. I know of one down in Australia, and it was very, very impressive. So once you realize that they have this, then I think, okay, well, then we can laminate anything to it. We could laminate neoprene, we could laminate, other higher insulating materials, so that it can perform more than just as a shading, ventilating, or operable system, but can potentially be sandwiched with other things to do that. And so we've been approached by engineers who are developing paper batteries, right, which I think is a great concept, because the paper batteries, they're trying to get to a point where, like Tyvek, building materials can be made, can be batteries in themselves. And so if those very thin materials or solar films that can also make energy can be applied to it, then virtually you can also insulate for sound or acoustics too.
At the beginning, the original projects are heavily influenced by natural tendencies, the grasshopper and the skin. How important is for you guys natural structuring nature to more recent projects? Like, is it still about trying to find that same efficiency that there is in the human skin and the grasshoppers breathing?
Okay, well, I'm going to expand your question a little.
Okay.
I think some people ask me if we, or some people try to categorize us as doing things that are biomimicry. And I don't actually try to mimic nature.
Okay.
At most, I would say that what we do is bio-inspired, right? And so there's things that give us ideas of how to do things, maybe directly, and in other cases, conceptually, right? The idea of something being waterproof or insulating become important in the forefront. And a lot of it is because it happens in nature, right? Not because another product does that or because we doesn't necessarily just need it, but we need it because our skin does it too. I mean, so why, you know what I mean, don't we, our buildings need to be waterproof, right? So does our skin, so there's all these different things. So the correlation seems almost obvious to me.
Okay.
Question? A common question I get, which is always funny, is the cost of the material or how expensive it is. It's actually a very inexpensive material. For the Bloom project, we used it's dependent on thickness, right? So metal is sold by the weight, and right now I'm using basically 3 different thicknesses. The critters are very, very thin, almost foil, like a thick, heavy foil. The Bloom was used a thickness that's very similar to flashing thickness, and then the EXO project, the structural one, is quite heavy. It's probably about a 1/16 of an inch thick. But the Bloom project, per square foot, the cost is only about, it's less than $3. It's about $2.50 per square foot, which really isn't that much considering the material and the smartness of it.
So I think what's really interesting is that the manufacturer themselves didn't know what this material could do, and it took you to be kind of questioning the thinness and the operation of that to say, hey, this thing that lives in a tiny box can really be this really big deal operating performance system. When was the moment that you looked in that thermostat box and thought, I wonder, like, what else can I do with this?
You know, for someone like me, the moment we got a sample of the material was a moment that everything opened up.
Gotcha.
Right, because we got, you know, they sent us these really bad samples, and I pulled it out and had writing all over it, and we just went outside and we put it out in the sun, and in LA that's an easy thing, and we just stood there and we watched, and all of a sudden it just started curling up, and it's just like, you know what I mean, all of a sudden it was like, oh my God, then we had to put it in the oven, then we had to put it in a way, we had to test it all kinds of places, right? It's like, oh, it works out too, right? And because you just don't believe it when you first see this material, right? But it was just so simple, and it's just doing this, and then it goes flat and goes up. And then we tried to heat it, you know, as high as we could to see if it wouldn't go back again, but we can't even get that temperature because this stuff works up to about 1,000 degrees, right? So my oven at my house won't even work, so it's like, okay, well, we need to go to some industrial oven. And at that point in time, it's not, you know, we're not going to damage the material in any kind of outdoor condition. And the funny thing is, everything that we test is a maximum of 120 degrees for us. I mean, if it goes beyond 120 degrees, I don't know what's going to happen for us. Yes?
What other materials have you experienced with that kind of give you sort of
Response to?
Yeah.
Well, the nitinol is another one, is the wire material. Another material that we're working with right now is actually really quite simple. It's a plastic. We're trying to move into plastics now to see if the plastics can operate. And the reason why is because it's much lighter weight, and it has more potential to use in the window systems. Right, so you can't use the plastics on the outside of a building, for example, because they're just very, very flimsy. It's like any kind of very thin film. But it curls much tighter, right? At, you know, a temperature's like almost instant curl. So it's a slightly different reaction. But the nice thing is a lot of our studies with the geometries and that kind of system can be translated pretty easily.
Today in our construction class, we learned about, I think it's like there's a moment where it just can't bend anymore. Like it just
with
snaps.
metal.
Has that ever been the case?
You're talking about structurally. So when it hits the point of deformation, it won't return? Is that what you're asking?
Yeah.
But it won't deform, for our material, it won't deform by itself to that point.
Or
You have-
that it bends so
Oh.
much that
It'll stop working?
stress so much that it adds.
The lifetime of the material right now indoors is something like about 18 to 20 years. For outdoors, we're still trying to test it because, again, they've never used it on outdoors, and we need to, and the testing required for that requires more money and approvals for building permit office. But it can operate millions of times before it ever fails, I think, as far as a curling. Is that what you're asking? If you actually bend the material, if I actually sat here and bent this material, it actually is fairly brittle. It's much more brittle than aluminum. It won't bend back. If you try to bend it back, it will break. So the point of deformation is I guess you'd say, is quite low for forced deformation. Yes?
You had a distinction between nitinol and the bimetals that you used in previous examples. Since bimetals are specifically two different alloys, correct? What are the two alloys that you prefer to use if it's not titanium?
The alloys are actually different percentages of similar materials. So one of the main materials is nickel, manganese, and a tiny bit of steel. And so the percentages are changed for the different sides.
And following up on extremities, are the goals for the firm to eventually push the limits and go into the industrial? So being able to use this material in factories or in enclosures for extreme?
That's a good question. And my idea is the goal is to get this thing to market, right? The fact that we can actually use it someday. But I'll say the reason why it's a difficult question is because I work with a university. And the university is not necessarily interested in getting things to market, right? So the support from the university stops after you hit a certain basic science level. And the funding also stops too, strangely enough. And so what we're trying to pursue is again, partnering with manufacturing in order to get that done. But that's why a lot of very, very innovative materials and ideas and things don't ever get to the market because of that problem. And it's combined between academy and government funding. Yes?
What kind of tools do you use to cut the material?
Laser cutting. Laser cutting is the best way to do it, and of course you need special laser cutters to cut metal. In LA it's easy for us because the aerospace engineering industry is very big. What we do in our own office, because we don't have that laser cutters, we use acid etching. So we acid etch just to do our early tests. What I didn't show you a lot is we do a lot of our early prototypes in paper and cardboard and plastic, in everything we can before we move to metal. So the number of models and samples that we make are huge compared to what you see in the end.
In the cutting procedure, does the laser temperature affect the material in any sense? In what way?
It curls it, right? Because it heats the material, and since metal is a conductor, right, it just moves through the material very quickly. So we use laser cutting facilities where they're willing to have someone sit there, and what they do is they keep putting weights down right after it. Because everything just starts moving and cutting, and sometimes it'll try to cut it when it's moving, and you get these distorted things, and there's a whole a learning process to how to do that whole thing.
Is there a specific way of knowing which direction the sheet would turn in particular, and starting since one side essentially is expanding at a greater rate than the other? So say for instance, if you were to cut it from it facing up, would it curl upwards if you just flipped it? If you did so, would the weight just hold it down?
No, the weight doesn't hold it down because it's light enough to actually curl, and it's hot enough. The laser is hot enough to do that. So sometimes, depending on the thickness of the material, we'll actually sandwich it between materials, right? So we'll sandwich it between cardboard or wood in order to cut it and to keep it weighed down. And most of the things we do, because they're big enough, the tolerance for mistake, it's very tolerant. So that you would rarely detect that kind of mistake. It's shockingly accurate in our systems, though. Again, you see these forms are fairly complex in shape, and every single time you think, oh God, what if something doesn't fit? Because that's the natural way we think of the old way of construction, right? You have to always design in tolerances to everything. 1/8 inch, 1/4 inch, 1/16 inch, to make sure that it all fits in the end. But what we've learned is if you design in tolerances like that, the thing won't fit and the shape won't take form. And so we actually have to work at a very high precision level with our computer models so that it will all match up. And the thing that's shocking to us in the end is it does match up, right? And it's quite amazing, this idea of tolerance for computer-aided fabrication. Any other questions?
Is this your business card?
This is, and everyone says I should have made it out of bimetal to curl, but this was actually done years before I even started in bimetal. But Bennett knows, I know Bennett a very, very long time. And the previous work I did has nothing to do with this kind of work, right? It was only the material itself that all these things, and the combination with available digital tools that made these things happen. But things I did before were very, very low tech, were very mechanical, but always kinetic, right? So the idea of one thing moving from one form to the other was a very, very big deal in the history of a lot of my work.
You got the samples, did you got the samples for the reason of kinetic? Like, were you going for, like, did you know that something was going to happen, or it just,
I looked for kinetic material. I actually did. I also have this kind of weird thing that came out of graduate school. When I was in graduate school, my thesis when I graduated was questioning why architecture had to be static. Why everything that seems to move seems to be so much higher performing. Our clothes fit our bodies better. We have materials that can, whisk off sweat and things like that. And our automobiles were much more higher performing. But our buildings were so backwards, right? Nothing is high performing whatsoever except it's just there. And so in graduate school I started to wonder why it can't move. Why can't things move? Why can't our whole building breathe and move or be mobile or change? And so that's something that stuck with me throughout my entire career. And the question, of questioning that over and over again, using different materials and using different methods. And so that's why I think when I started to look for smart material, the thing that was so enticing to me was the fact that it moved. I mean, and you didn't have to do anything, it just moves, right? And the fact that we have sun and we have heat and we have all these things going on in an environment, it's going to move. So it's also a different way, indirectly, although this was not intentional, of how we start to think of facade systems, right? And how facades are. So each time you look at it, it is indeed different, but it has nothing to do with human occupation. In some ways, it is just the way it is, almost like something that has a mind of its own. It just keeps moving throughout the day.
Do you ever plan to look towards the ideas of enclosure in kineticism as well? Or are you strictly looking at facades as of right now as the major focus of your work?
Enclosure meaning?
Well, structural support, things that are supposed to take load. Do you consider them to have any kind of kinetic potential?
It's hard because the structural things that I worked on are not kinetic during regular time. It was kinetic during the assembly process. It's hard to make them do both. I mean, the structural, you ask any structural engineer and they want to stay away from that, like anything. But a lot of it, I think, is because of the liability issues that are determined by code, right, and what they have to design to for code. The nice thing is working with like Borough Happold and Arab Engineering on some of these speculative projects, they're willing to push the limits of it because we don't have to worry about code for these. Some of it, I have to say, is very edgy and, nerve-wracking when we're putting these things together because they're so innovative even as structures. But it's hard to say that we can actually do both beyond like the Slinky project or something and where that goes. A lot of the projects that I work on, there's a combination of of having an end in sight, right? A top-down type of attitude versus a bottom-up method of design. Most of the stuff we do is bottom-up, and we have no idea if it's ever going to be really useful, but it's just something we can do, so why don't we design it, why don't we build it? And so in my firm, I have the luxury of not having clients telling us what we can or can't do, or what we need to be doing. And so we just kind of pursue some ideas and stuff that we want to do. And that's what makes it, I think, enjoyable. And the freedom to think like that makes us, allows us to be more innovative.
So thanks again for very inspiring, right? And also entertaining. Great lectures.
Thank you.